9.5 hours, that's how long the ground stayed open. On the night of August 12th, 2026, the summit of Kīlauea tore itself apart for the 53rd time in a row, and lava climbed into the Hawaiian sky until it lit the underside of the clouds orange. And here's the part almost nobody is talking about. Roughly a day earlier, something shifted deep beneath the ocean floor, miles offshore, in a place most people have never heard of. A jolt in the dark. And then the volcano did exactly what it just did. Coincidence? Maybe. But the scientists who study this mountain for a living are watching one specific signal right now. And if you understand what that signal means, you'll never look at a volcano the same way again. Stay with me, because by the end of this, you're going to understand something most people watching the news tonight completely missed. And if you like knowing what's actually happening under your feet before everyone else does, hit subscribe, because this is what we do here. Let's start with what actually happened, because the timeline matters more than you'd think. Kīlauea sits on the big island of Hawaii, and it has been erupting on and off since late December of 2024. Not one continuous river of lava, but something stranger. It goes in bursts. It fills, it pressurizes, it erupts in a violent fountain, and then it goes quiet again. Then weeks later it does the whole thing over. Geologists have a name for this. They call it episodic. And Kīlauea has now done it more times in this single eruption than it has ever been recorded doing before. Think about that. We are watching a volcano set its own record. Live, one episode at a time. Episode 53 began at exactly 3:45 in the afternoon, Hawaii time, on August 12th. The lava came up out of the north vent inside the summit crater, a place called Halemaʻumaʻu, which sits inside Hawaii Volcanoes National Park. And when I say the lava came up, I don't mean it oozed. Earlier episodes in this eruption have thrown molten rock more than 500 feet into the air. That's taller than a 50-story building, made of liquid stone, glowing at temperatures that would vaporize almost anything you can imagine. By the time the fountaining wound down late that night, the height had dropped to somewhere around 80 to 100 feet, still enormous, but the beginning of the end for this particular burst. And then, at 1:23 in the morning on August 13th, it stopped. 9.5 hours start to finish. The mountain exhaled and went still. And when the fountaining ended, the observatory that watches this volcano lowered its alert level from warning back down to watch. A quiet, bureaucratic little change that actually means something important. It means the immediate danger passed, and the waiting began again. Now, if that were the whole story, it would be a beautiful piece of nature and not much more. But it isn't the whole story. Because to understand why Kīlauea keeps doing this, you have to understand what's happening where you can't see it. And that's where this gets genuinely fascinating. Underneath Kīlauea is a chamber of molten rock, magma. It rises up from deep inside the earth and collects in a reservoir beneath the summit. As more magma pushes in, the ground above it literally swells. It inflates, like a balloon filling with air, except the balloon is a mountain and the air is molten rock. Instruments on the surface can measure this swelling down to fractions of an inch, and here's the pattern the scientists have learned to read. When the summit inflates to a certain point, the pressure gets high enough that the magma finds its way out. It erupts. And the moment it erupts, all that pressure releases, and the ground deflates. It sinks back down. Then the refilling begins again, and the whole cycle resets. So the eruption you saw wasn't random. It was the release of pressure that had been building for weeks. The fountaining you'd see on a webcam is really the visible ending of an invisible process that started long before. And this is the first curiosity loop I want you to hold on to, because I'm going to come back to it. The question isn't really, why did it erupt? The question is, what will it do next? And can anyone actually predict it? Before we get there, let me pull the camera way back. Because to really understand this volcano, you have to understand where it came from. And the answer is one of the most beautiful stories in all of geology. Most people look at the Hawaiian Islands on a map and see a scatter of tropical dots in the middle of the Pacific. What they're actually looking at is a trail of fire left behind by something that has been burning in the same spot for tens of millions of years. Deep beneath the Pacific, far below the ocean floor, there's a plume of intense heat rising up from inside the Earth. Scientists call it a hotspot. It doesn't move, it just sits there in one fixed location, melting rock and pushing it toward the surface. But the ground above it does move. The entire Pacific plate, the vast slab of the Earth's crust that carries the ocean floor, is slowly, constantly drifting to the northwest, about as fast as your fingernails grow. And that combination, a fixed source of heat below and a moving plate above, is what built Hawaii. Here's how it works. The hotspot punches a volcano up through the plate. The volcano grows, erupts, builds an island, but the plate keeps drifting and eventually it carries that island away from the hotspot. Cut off from its heat source, the old volcano goes silent, and a new one begins to form behind it, right over the hotspot again. Do that over and over for tens of millions of years and you get exactly what we see. A chain of islands, each one a little older than the next as you travel northwest. In fact, If you follow the trail past the islands, you can see it continues underwater as a line of drowned mountains, seamounts, stretching almost 6,000 kilometers across the Pacific floor. That's a nearly 6,000 kilometer scar, a record of where this hot spot has been for millions and millions of years. This is why the islands feel so different from one another. Kauai, up in the northwest, is old and deeply weathered, carved into dramatic green canyons and razor-edged ridges by millions of years of rain. The Big Island, in the southeast, is young, raw, still growing, still bleeding lava. It sits directly over the hot spot right now. That's why it's the one erupting. And Kīlauea, the volcano putting on tonight's show, is one of the youngest and most active pieces of the whole chain. It is, quite literally, the leading edge of a process that has been running since before humans existed. So when you watch that lava fountain, you're not just watching an eruption. You're watching the exact same machine that built every island in Hawaii. Still running, still doing the only thing it knows how to do: building. Now hold that thought, because there's a twist to this story and it's hiding underwater. The hot spot that built the Big Island hasn't stopped. It never stops. And that means somewhere out beyond the coast, it's already working on the next island. This is where that mysterious jolt from the beginning comes in. Off the southeast coast of the Big Island, deep beneath the waves, there's a submarine volcano. For a long time, it carried a Hawaiian name, and it has been slowly, patiently constructing itself for tens of thousands of years. One day, in the far future, tens of thousands of years from now, it may break the surface and become a new Hawaiian island. But it is not there yet. It's still a mountain hiding under the sea, and it announces itself the only way it can, with earthquakes. The night before episode 53, that undersea volcano produced a magnitude 5 earthquake, a real one, sharp enough to stand out. And in the hours that followed, the summit of Kīlauea showed a noticeable jump in its inflation. The swelling sped up, and then the eruption came. So let me ask you the question the experts are quietly asking. Did the earthquake out at sea have anything to do with the eruption on land? Because on the surface, the timing is striking. A jolt offshore, a spike in pressure at the summit, and then lava. It looks like a chain reaction. It feels like a chain reaction. But here's where I have to be honest with you, and where a lot of channels would just tell you what you want to hear. We don't actually know that one caused the other. In science, two things happening close together in time is not the same as one thing causing the other. The magma beneath Kīlauea was already refilling. The pressure was already climbing back up before that offshore quake ever happened. The eruption may well have been coming regardless. The earthquake might have been a nudge, or it might have been a coincidence that just happened to line up in a way our pattern-seeking brains find irresistible. And this is exactly the kind of thing scientists have to be careful about, because getting it wrong in either direction has real consequences. I want to know what you think about this, genuinely. Drop a comment and tell me, do you believe that distant earthquakes set off the eruption? Or do you think it was going to happen anyway and the timing just fooled us? I read these, and this one's a real debate, even among people who study volcanoes. Now, why does any of this matter beyond being interesting? It matters because reading these signals correctly is the entire game when it comes to keeping people safe. And Kīlauea, as dramatic as it looks tonight, has shown us exactly how high the stakes can get. Because this same volcano, not that long ago, did something very different. Something that people who live on the Big Island will never forget. Let me take you back to 2018. Because if you think of Kīlauea as a gentle giant putting on a light show, this is the story that will change your mind. In the spring of that year, the eruption didn't stay politely at the summit. It moved. The magma pushed sideways, down through what's called the volcano's rift zone, and it surfaced tens of miles away from the crater, in the middle of a residential neighborhood. In a community called Leilani Estates, the ground literally cracked open. Steaming fissures tore across streets and through yards. Over the following weeks, 24 of these fissures opened up, and out of them came lava, not 500 feet in the air for a few hours, but pouring out across the landscape for months. The numbers from that eruption are staggering. Around 60,000 earthquakes rattled the volcano during that period. 24 fissures erupted. The lava destroyed roughly 700 homes. It displaced more than 2,000 people, families who watched, in some cases live on the news, as the molten rock crept toward their front doors and swallowed everything they owned. It buried 30 miles of road. And when it was finally over, it had poured so much lava into the sea that it added around 875 acres of brand new land to the island. Think about that contradiction for a moment. The same event that destroyed 700 homes also created new ground where there had only been ocean. Destruction and creation from the exact same source at the exact same time. That is the other face of Kīlauea, the one we're not seeing right now. And the only reason tonight's eruption feels like a spectacle instead of a tragedy is a matter of geography. In 2018, the magma found its way into a neighborhood. In 2026, it's coming up inside the summit crater, contained within the national park, far from anyone's home. The mountain hasn't become gentler. The lava just happens to be surfacing in a place where it can't reach us. That distinction, where the lava comes out, is sometimes the entire difference between a beautiful night and a catastrophe. And here's a detail people underestimate even when the lava does stay put. Even when it can't reach a single house, the eruption sends something else into the air that travels far beyond the crater. When that much molten rock is exposed and fountaining, it releases volcanic gas, sulfur dioxide mostly. And when that gas mixes with sunlight and moisture in the atmosphere, it creates a haze the locals have a name for. They call it VOG, volcanic smog. On days when a fountaining episode is running strong, that haze can drift downwind across communities. And for people with asthma or heart conditions, it's not just an inconvenience, it's a genuine health hazard. So the reach of a volcano is always bigger than the reach of its lava. The rock stays in the crater. The breadth of the mountain travels for miles. So how do the scientists stay ahead of all this? How did they know in 2018 to get people out? How do they know tonight that the danger has eased? This is the part that I think is genuinely amazing, and almost nobody outside the field understands how it actually works. Watching a volcano is not about staring at the crater and waiting for lava. By the time you see lava, it's already too late to be surprised. The real work happens through a web of instruments spread all across the mountain, each one listening to a different whisper. First, there are the seismometers. These are the ears. They listen for earthquakes, and a volcano getting ready to erupt doesn't stay silent. As magma forces its way up through cracks in the rock, it triggers swarms of small earthquakes. When scientists see the quakes clustering, migrating, changing character, they're effectively watching the magma move underground in real time. Remember those 60,000 earthquakes in 2018? That wasn't just noise. That was the mountain telling its story to anyone with the instruments to listen. Then there are the tiltmeters. And these are extraordinary. A tiltmeter is a device so sensitive it can detect the ground tilting by an amount almost too small to imagine, changes far finer than anything you could ever feel standing on the surface. Remember how I said the summit swells as magma fills the chamber beneath it? Tiltmeters are how they measure that swelling. As the ground bulges upward, it tilts ever so slightly, and these instruments catch it. When the eruption releases the pressure and the ground sinks back down, the tilt reverses. Watch the tilt, and you're watching the volcano breathe. In, then out, inflate, then deflate. Alongside the tiltmeters or GPS receivers, the same basic technology that guides your phone, but tuned to a precision that can detect the whole mountain physically stretching and shifting as magma moves inside it. And then there are the gas sensors, sniffing the air for that sulfur dioxide, because a change in how much gas the volcano is releasing can be an early clue that something is shifting deep below. Put it all together, seismometers listening, tiltmeters feeling, GPS measuring, gas sensors smelling, and you get something remarkable. A volcano that can't hide. Every one of these instruments catches one piece of the puzzle, and the scientists at the observatory weave them together into a single picture of what the mountain is doing beneath its skin. That's how, in 2018, they could warn people before the worst of it. And that's how, tonight, they can tell us the pressure has eased and the alert level can come down. But, and this brings us right back to the question I promised I'd return to, all of that monitoring runs into one stubborn wall. It can tell you the pressure is building. It can tell you an eruption is likely soon. What it cannot do is tell you the exact hour. The answer to, can we predict it, is a fascinating kind of yes and no. And it tells you something deep about the limits of what science can do. Scientists can absolutely see the pressure building. The inflation is measurable right down to those tiny tilts. They can watch the summit swell back up after each eruption, and as it approaches the level where past episodes have started, they can say with real confidence that another one is likely soon. In this eruption, the episodes have been coming roughly on the order of once a week or so, sometimes closer together, sometimes further apart. So, in a broad sense, they can tell you the mountain is loading up again. What they cannot do is tell you the exact minute the fountain will start. They can't hand you a countdown clock. The final trigger, the specific moment when the pressure crosses the line and the rock breaks through, depends on details too small and too deep to measure precisely. It's the difference between knowing a pot is going to boil and knowing which exact second the first bubble will break the surface. The physics is certain, the timing is not. And that gap, that narrow, stubborn gap between we know it's coming and we know exactly when, is where all the difficulty and all the danger of volcano forecasting lies. Now here's a pattern interrupt for you, because I don't want you to think this is only a Hawaii story. Kīlauea is one of the most closely watched volcanoes on the entire planet. There are instruments all over it, cameras pointed at it around the clock, scientists studying its every twitch. It is, in a strange way, the best case scenario. We understand it about as well as we understand any volcano on Earth. And even here, even with all of that, the best anyone can honestly say is soon, not now. So think about the volcanoes we don't watch that closely. Think about the ones in remote parts of the world with a fraction of the monitoring. Think about the millions of people who live in the shadow of mountains that get a tiny sliver of the attention Kīlauea gets. Mountains with no dense web of tiltmeters and gas sensors listening to their every move. That's the uncomfortable truth hiding inside this beautiful eruption. If the well-studied one still keeps its secrets, what about the ones nobody is really watching? Let me take you back underwater one more time, because there's a bigger picture forming, and I don't want you to miss it. That submarine volcano offshore, the one that produced the earthquake, has been showing its own activity, clusters of small quakes along its flanks. Now, an underwater volcano rumbling is not by itself a reason to panic. These are small events, and this mountain has been quietly building for a very long time without any dramatic eruption that anyone has ever witnessed. But it has the potential. Somewhere down there in the dark, the same hot spot that feeds Kīlauea is feeding a future island, one earthquake at a time. And every so often, its activity and Kīlauea's activity seem to brush up against each other, close enough in time to make you wonder if they're talking to each other through the rock. That's the thread scientists keep pulling on. Not because they expect a catastrophe, but because understanding how these systems connect, or whether they connect at all, is how you get better at reading the warning signs. Every eruption, like episode 53, is a data point. Every earthquake that lines up with an inflation spike is a clue. Slowly, one episode at a time, the people who study this are building a picture of how a volcanic system actually breathes. And here's something I find genuinely moving about all of this. We are living through a piece of geologic history in real time. Most of what shapes our planet happens on timescales so slow that no human ever sees the beginning and the end. Mountains rise over millions of years. Continents drift at the speed your fingernails grow. The Hawaiian chain took tens of millions of years to build. But Kīlauea, right now, is putting on a show fast enough for a single person to watch, night after night, episode after episode. You can pull up a webcam and see the Earth building itself. That almost never happens. We are, by pure luck of timing, alive during one of the most active and best documented eruptions in the modern record. So let me tie the loops together, because I made you some promises at the start. I asked whether that distant offshore earthquake caused the eruption. The honest answer is that we can't prove it did. The pressure was already rising, the eruption was likely coming anyway, and the timing may have simply lined up in a way that fools the eye. It's a maybe, and an honest maybe is worth more than a confident lie. I asked whether we can predict the next episode. The answer is that we can see it loading and say it's likely soon, but no one can give you the exact hour, and that gap between soon and now is the whole challenge of living beside a volcano. And I told you the scientists are watching one specific signal. That signal is the inflation, the swelling of the summit as the magma refills, measured by those impossibly sensitive tiltmeters. Right after episode 53 ended, the deflation showed up right on cue, the pressure released, the ground sank, and the alert level came down. And now the clock resets. The refilling begins again, which means that somewhere beneath Hawaii Volcanoes National Park, at this very moment, the pressure is quietly climbing back toward the line. And when it crosses that line, episode 54 will begin, and we'll all get to watch the Earth do the single most dramatic thing it knows how to do. That's the thing about a volcano like this. The eruption is never really over. It's just resting, loading, getting ready to remind us who's actually in charge on this planet. And it isn't us. This same mountain built an entire chain of islands across 6,000 kilometers of ocean. It swallowed 700 homes in a single summer and then handed back new land carved from the sea. It's a creator and a destroyer wearing the same face. And right now, tonight, it's just catching its breath before the next act. If you found yourself learning something tonight, if you now understand a little more about what's happening beneath that glowing crater than you did 15 minutes ago, do me a favor. Hit that like button. It genuinely helps more than you'd think. And subscribe to W for Weather so you're here when episode 54 begins. Because when it does, we'll break it down together, live. And leave me that comment, earthquake trigger or coincidence. I want to hear your call. Take care of yourselves, keep looking up, and I'll see you on the next one.